Hello, my name is James Obenmeyer, and this video is going to serve as a little walkthrough of the thoughts and processes of how I made the Pipe Dream, which was my 7 week long capstone project for my music minor. The original inspiration for this project was based on the Music Box, where it was this standalone installation that was able to produce music on its own. The only real decisions I had in my head coming into this project was I wanted it to be its own standalone installation. So I wanted it to be able to play on its own. And I wanted to preserve that almost magical experience that is had with a music box where it appears to just play music by itself. Um, I wanted to preserve a dreamlike quality of tone, something ethereal and something that would be built on the idea of building a soundscape. Some thoughts I was having as to what it would sound like is reminiscent of someone rubbing their finger along the edge of a wine glass, so that glass-like pure kind of a tone, or the bowed vibraphone would be another good example of this sort of idea I had of what kind of sound it would come with. So to start getting an idea of how I was actually going to test some of these things, the first thing I did was just took a violin bow and got behind a vibraphone and started messing around with it. Um, I was also alongside some basic experimentation of different kinds of objects that can make different kinds of sounds and different kinds of friction materials that could excite those different sounding objects. I was doing some research on some prior art that already existed, um, in terms of like friction idiophones, and different kinds of idiophones and what kind of instruments were out there, what kind of musical robots people were already making. And that sort of outlined a line of thought where I had a few objectives, right? So I needed to find the sound of my instrument. I needed to pick an actuation method to actually sound whatever object I chose for that first objective. Um, and then I needed to integrate the two of them together. So if I have a vibraphone bar as the chosen object, for example, and a bow, violin bow, how am I actually going to make a musical robot combine those things to play it together? So the sort of outline that I was having was I had two main methods in my mind. It was either mechanical actuation with some kind of a friction surface, or electromagnetic actuation, which I will get to in the parts of the video in the future. So what I'm using to put this video together was a bunch of various videos that I have, that I took throughout the process to sort of give way. The biggest thing that I want this video to serve as is just like a visual and auditory documentation of the process. I noticed when I was doing a lot of research that there were many papers that were available, but there were very few videos which gave that visual and audible sort of experience to what was going on. So I just wanted to have this all in one place and document the progress that was made so far in this project. So without further ado, here's the video. So now that I've researched some instruments that use similar methods to the instrument I'm going to be making, it's time to act on the first objective that I've set up. That objective being finding the sound of my instrument. So that's going to involve testing a lot of different sounding objects. The way I'm going to go about this is I have this crude little experimental fixture. It's just a piece of extrusion. There are bolts with small rubber pads that affix it to the channel on the inside, and there are two small dowels, about 6 inches long, one with a bolt that's clamped in, which holds one end of a piece of twine, and a second hole for a second bolt to affix the other side of the twine. Basically how this works, I have a vise on the side here, so you clamp the setup into the vise, and the front one will go underneath the first node of the sounding object, and the second one goes underneath the second node on the sounding object. So you're able to adjust this where you need to, and then tighten it down wherever that node might be. So for an example, I have this pipe here. I've tuned this pipe to a B flat, and you'll hear that in a second. I've drawn the two nodes onto here, and so having the knowledge of where those two nodes are, I can put the first one on this first dowel, adjust the second one to where the second dowel's location is, quickly adjust it, and then as a little test, you can hear it is allowed to freely resonate. Now, if that's not in the right place, so let's say I adjust this to where it's not on the second node, you can hear that without the nodes, you have a significantly damped response. You're not going to get the same kind of free vibration that you heard earlier. So I'm going to be using this to test a bunch of different materials. I have a couple tubes here, which I've tuned all to B flats. I even have a solid rod as well that I tuned to a B flat. That was mostly as a test to see whether I was able to tune things by hand. I have some other objects that I didn't tune by hand that I'm also going to be testing. Most of them are large like this, quite heavy, very dense materials. It would take a very long time. I'm using hand tools, so cutting through this would take a significant amount of time. Basically, my plan for each of these sounding objects is to first strike it with a mallet. I have a cloth mallet here for a couple different reasons. I'm looking really to find and excite the fundamental of each sounding object. And I've noticed that when you hit an object with a harder kind of material, so I'll use the back of the mallet as an example, you hear a lot of those higher overtones a lot louder. So I'll give you an example. It's the difference between that high sort of clink sound, you get that signature bell kind of sound, versus a soft mallet. I think it's able to excite the fundamental a lot more noticeably. So that's going to be the first sort of impulse. And then I'm going to be using a violin bow on two kinds of surfaces. So on each of these objects, I've placed a small piece of a leather pad. It's just a leather mouse pad. I've cut a strip off of it and super glued it. And so what that's going to do is give a different kind of surface for the violin bow to interact with. The violin bow is going to be applied with a fresh amount of violin bow rosin before each test, just for consistency. So the first thing I'm going to bow is just the direct edge of the pipe, so you can hear. It doesn't give as much of a response. You have to be very careful. If you go completely flat, you can get this kind of a response. So I'm going to bow it a couple different times just on the direct edge, and then I'm going to use the leather pad to test how a different kind of a surface might change the sound of it being bowed. So you can hear. So without giving too much away, that's generally the plan. We're going to record all of these sounds. I'm going to record a video of how I did it as well, so you have a visual. And then we're going to run each of those signals through a spectrogram analysis and talk about what we found and move forward to see if we can find this sound that I'm looking for in my instrument. Let's get to it. You can hear that it's a pretty strong response. And it is proportional to how close it is to the actual electromagnet. So when you get very close, you can tell. And if you shift it to a different part on the pipe, you get a much smaller response. So it seems like the magnet needs to be placed at a nodal or an antinodal point on the pipe, which is either at either end or in the center to excite its fundamental. So if we were just to estimate where the center would be, somewhere like there, then you can hear that same response again as we get closer. So one of the cool things about using these magnets, and these are just standard neodymium magnets picked up from Home Depot, is that you can excite materials that aren't naturally ferrous. So this, for example, is not a magnetic metal. I just superglued a magnet here to it. So we have the same setup as before, except the resonant frequency of this pipe is closer to 1,113 hertz. We have the same voltage flowing through here. So let me contact. It's difficult with one hand. We have about 7.94 volts coming out. Our electromagnet is attached. And so this square tube, the response you get is something like this. Now, I think because of the way this is set up, the tube is a little damped, so you can hear that quick drop off. This is an example. You know, the closer you get, you can really get a pretty serious response. And just like everything else, you know, the closer you get to it, the louder the response, the more far away. Very subtle. So you can do some pretty cool thing with some cool things with the positioning of this. And the volume is also proportional to the current that you're running through your electromagnet as well, which is something to keep in mind. If you pass by, you get these very very interesting. So here's a very exciting update about the electromagnetic prototype. So this is sort of my prototype rig V2. We have the sounding bar, and I had originally tuned this bar to a D6, but with the addition of the neodymium magnet at its antinode right in the middle, it seems to have tuned down a little bit, so it's a little bit flat of a D6 right now. But I basically just have it free hanging on a string. It seems like from what I could rig up, a string gave the most sort of free resonance response. When I tried hooking it up more mechanically with just like attaching a screw to the hole here at its node, it seemed to give a damped response, which is not what I was looking for. So here it's very simply rigged. You can see there's a little bit of space, and that's just because of how the string tension is on there. But it gives it a nice sort of free ring. And you can see that it truly is free rigging. We have the electromagnet mounted right in the center with just a little bit of space between that magnet there. And so I have it hooked up to this audio amplifier. We have Room EQ Wizard open. So that's supposed to be about 1174 hertz is what D6 is. So the actual resonance from, experimentation I found was actually 1159 for this tube, which is, a little bit flat right there. So I'm going to send a sine wave into it, and what you're going to hear is the audio amplifier amplifying that signal to about 5 volts, which is what the electromagnet is rating for, and you'll hear the response. So let's get that. So the next step in my testing process is to move away from the Room EQ Wizard software and get it up and running with an Arduino. So the first thing I did was a very basic code. I used the tone function to generate a tone out of pin 6 with a frequency of 1,159 hertz, which is the resonant frequency of that bar at the moment. And now it outputs out of pin 6 a square wave because it's a digital pin. So with the setup, I upgraded this so we could get a better sound. So this is a 10 kilogram holding force electromagnet. I upgraded from the old 5 kilogram version. We also have a heavier version here, so I'll give you sort of an idea of what this sounds like. So I'm just plugging the electromagnet directly into the Arduino here, and it sounds like this. So here I have a very basic transistor circuit. I'm using a TIP120 transistor. So here the gate is connected to the output pin on the Arduino, which is pin 6 according to the code. The source is connected to ground, and then the drain is connected to the electromagnet. So if you plug the electromagnet in here with our power supply, this is the response that you get. One of the primary issues I'm facing with getting a clean sound out of these pipes is the quality of the signal that I'm sending to the electromagnet. Ideally, I would be able to send a sine wave, but it's very difficult to generate a sine wave with something like an Arduino because it wants to send digital signals, which is just on or off. A square wave doesn't sound great. I'll show you what basically just sending a square wave through sounds like. So if we connect this here, so you can hear that we get great sustain, but the initial sound sounds very harsh. You can hear some of the higher harmonics that are messing with the quality of the sound that's coming out of the bar. So the first thing I tried, which is what I have here, is third order, just passive RC filtering. So this is a low pass filter. The cutoff frequency is just about 1500 hertz. The signal that I'm trying to send through is about 1174 hertz. And even with one round of passive filtering, so here I'll put the electromagnet into the second set of resistors here. So there you can see there's pretty significant loss in the volume of the sound. However, it does sound a lot cleaner after going through 2 rounds of filtering. And if we add a third stage here, you'll hear even more loss, but a additionally cleaner sound. So that's where I'm at with this. What I have going here is I have a power supply supplying 12 volts at 5 amps. That goes into a TIP120 transistor, which is amplifying the square wave that comes out of the Arduino. And then that amplified signal gets sent into our filtering network. I tried it the other way around, where you feed the square wave directly into the filtering network and then amplify the output of that. However, I was getting a lot harsher overtones using that method than I am with this, so it seems like filtering after amplification is the better method. So here, this is a test I was doing that just outputs a simple PWM signal. The duty cycle fluctuates between 0 to 100% at a specific period. This period corresponds to a frequency of around 1174 hertz, which translates to a D6 to that bar. It just uses the basic analog write function. The issue that I've experienced with this is it sounds almost scratchy. Something about those upper harmonics cause this weird effect on it. So I'll show you right here. I'll plug this in and you can hear it for yourself. Sorry, there are lots of loose connections in the breadboard, so it's tough troubleshooting sometimes, but you can hear how those upper harmonics are adding some unwanted scratchy noise. So gonna look into some other options besides just using the analog write function to send some kind of a modulated square wave signal to the bar. So pretty big update with the project. Here I've got code that reads in MIDI information from Ableton, and then when it senses a note on, it prints it in the serial monitor just so I can track it, and when it senses a note off, it also prints that. When it senses a note on, it triggers this update modulation function here, which sends a PDM signal out of pin 6 and through a simple amplification circuit over to the electromagnet to sound the bar. So here I've got pin 6 coming out of the Teensy going to a simple just MOSFET transistor here. That's hooked up to an external power supply, so that's just going to amplify the signal a little bit for the actual bar itself. And the power supply gives 5 volts. So far, the only issue I have with this setup is it's not drawing a lot of current. The electromagnets are rated for 5 volts at 1 amp, and I'm only getting on the scale of 2 milliamps right now. I'm going to look into why that is and see if I could scale up the current a little bit so that we can get a louder noise. But I'll show you what it sounds like for right now. So if we open Ableton, I have this little MIDI clip here which just repeats this note. In the code, I have it set to the target note. 98 translates to a D6, which is what the bar is tuned to right now. And so if I click play, so here's another big update. We have polyphony. So I don't have any amplification circuit coming out here. I just have both electromagnets coming straight out of the pin. So it's pin 6 and pin 7 for these two notes. And they're both connected to ground. That's the entire circuitry. You have the two electromagnets right there. This one isn't going to be as loud because this one is only rated for a 5 kilogram holding force, while this one's rated for a 10. When we get the other electromagnets in, I will set them all up with the 10, so they'll all be playing at the similar level. So basically, all you have to do to change the code here is you add a new target note, which in this case is 99, and then you just add a new modulating function here. And so all the same MIDI code is the same. It's just reading and then running the update modulation code in the loop, depending on which one's sensed. So you have a target note 1, target note 2, exact same code, just 1 and 2 now. And then if you come down to the modulation, you have your modulation code, which sets up all the initial parameters here. And then if it's modulating 1, it runs this code. If it's modulating 2, runs that code. So now I have here set up with D and D sharp 6, which is what these two bars are. And if I play it, you can hear. So there you go. And if I play them at the same time, they're played at the same time. So now we've gotten the Teensy board to be able to read MIDI, and then based on whatever note comes out, I'm able to send a viable signal to the respective tone bar. All of the electromagnets needed for 1 full octave have come in, and I've created a new version of the instrument, the actual frame itself for the instrument. And so the next step in this testing, which is one of the last ones, is trying to figure out which magnet works best. So I've gotten here a bunch of different magnets. So these are different kinds of neodymium magnets here, of all varying sizes. They range in size from as small, here, I'll just take all of them out. They range in size from something that is that small to something that is the same size as the actual electromagnet itself. So going into this, some of the theories that I have is each electromagnet generates a magnetic field around the magnet, right? And so if you get a magnet that is extremely strong, you'll have a stronger interaction. But if you also get a magnet that has more surface area to interact with that magnetic field, then you'll also get a stronger response. I have also the electromagnets that are all rated for 5 volts at 1 amp. The first one has a holding force of 5 kilograms. The next one has a holding force of 10 kilograms. And then the step up above that has a holding force of 25 kilograms. In my earlier testing, I found that 10 kilograms gave the best sort of in between, because the 25 kilogram holding force magnet was quite large and the magnets I had available were quite small. And so there wasn't enough of the magnetic field that was being generated by the stronger magnet to actually interact with that magnet. So having the 10 kilogram holding force created a better interaction overall, even though it had a technically weaker rating associated with it. So right now I have the original small neodymium magnets that I was using before. I believe these are just from Home Depot. They were lying around my apartment. I have these, which has plenty of assorted sizes for neodymium magnets. I also have these ceramic disc magnets. So some of the things I'm noticing right off the bat, if I were to just try and guess the kind of response that I'm going to get, the neodymium magnets seem to be much stronger, like per unit of size. So if I get a neodymium magnet of this same size, I'm expecting the neodymium magnet to be much stronger than the ceramic magnet. The pros and cons here: neodymium magnets are more expensive. The ceramic disc magnets are very easy, very cheap. So if this is a viable product, then this would be a great option. But we'll get testing and see what happens. So just as sort of an example of what we're working with here, this is the new frame. I have 12 of the 10 kilogram electromagnets rated for 5 volts at 1 amp attached to here. I have the Teensy board, which is loaded with the Arduino code. So when I play something like this out of it, which is a D and a D sharp 6, which is what these two bars are tuned to, we hear something like this. So pretty weak response. I don't have it hooked up to any kind of transistor sort of switching network to connect it to a external power supply to give it some more power. But the bars are sounding very similar, and right here you can see we have the ceramic disc magnet and the original neodymium magnet attached to either bar. So we'll just quickly edit this, delete that, and we'll duplicate this so that you can hear the notes back to back and what that sounds like. Let's just fix the circuit here for a second. So I have the connections coming out of pins 2 and 3. The ground is connected to the ground back here. And that's running to the first two magnets here, which again connected to the ceramic disc on the D and the neodymium on the D sharp. So we'll listen to what that sounds like. So comparing these two, it seems like the ceramic disc magnet gives an equal response, if not better, than the neodymium magnet. That's great to hear. The ceramic disc magnets are much easier to get. They're cheaper and more available. And my theory behind why is, although the neodymium magnet is stronger, like I was saying before, the ceramic disc magnet is a little bit wider. And you can sort of see here, the electromagnets have this core that concentrates the magnetic field around the center area. The neodymium magnet is pretty small, and it is a little bit smaller than that core. However, the ceramic disc magnet is thicker, and I think more of the magnetic field is able to interact with that magnet, causing a better response. So here in front of me, I have all 12 of the tuned bars, which represents a full octave from C6 all the way to B6 chromatically. And so the process of making these bars, I've gotten down a little bit to a science now that I've made enough of them. So basically, the first step is to cut your bar roughly to length. The way I like to get a rough estimate is I just cut it to the length of the last bar that I just cut out. So if I'm cutting out B6, for example, I'll first cut a tube to the length of A sharp. And then you take it to the file, after you make the cut, and you file it down nice and flat, and then you hit that with a tuner to see where you're at. And then you start the process of filing it down, hitting it with a tuner, filing it down, hitting it with a tuner until you hit that mark and make it in tune. Um, then, after you get it in tune, you need to measure the center of the bar, which represents the antinode, and you super glue the magnet to the center of that line. That adds mass to the bar, which changes the resonant frequency, makes it a little more flat. So then you take it back to the file, you file it down, hit it, file it down, hit it, file it down, hit it until you're moving that mark back in tune. Once you get that tuned up, you take it to the measure it again and mark out where the nodes will be. The nodes are about 22.42% of the entire length of the bar in from the end. So basically, you take the length of the bar, you multiply it by 0.2242, and then you measure that distance from either end of the bar inwards. And that will give you your two nodal points. The way I'm mounting the bar is just with two strings that go on the insides of this. So I have a drill bit in the drill press, and you punch a hole through on either side, right at the nodal points. And then that usually will change the resonant frequency just a little bit. In my experience, it makes the bar a little more flat. And so you take it back to the file it, hit it, file it, hit it, file it, hit it until you move that line back to the correct tuning, and then that gives you the final bar. I have the ceramic disc magnets on the center of them, and we have a full octave now. So at this point, we bring it to the instrument, assemble it all together, and start doing some of the final circuitry. Very exciting. Just for reference, each bar took me an average of 30 to 45 minutes, depending on how lucky I got with guessing the initial length of the bar. But that whole system of going back and forth and back and forth and back and forth was quite a lengthy process, especially if you're doing it all by hand, which I'm doing it all by hand. So I definitely recommend, to make this a little faster, having something like a bandsaw to cut your aluminum and some kind of a belt sander to grind it down a little faster. That'll definitely cut the processing time. I will say, though, that for the fine tuning, sometimes your results can be a little less predictable than you would think. Like, for example, removing material at the nodal points to put the string through, I expected to make it sharper because I'm removing material, but I made it flatter. And stuff like that could change if you're using material, like if you're using equipment that removes material quicker than hand filing or hand tuning these things. So doing it by hand sort of made the fine tuning a little easier, in my opinion, because I was able to remove less material at a given pound time and move with the changes. So even if something surprised me, I wasn't removing enough material for it to have made a significant impact. I will say with one of the bars, I did get a little overzealous and I removed a little bit too much material, which made the bar a little sharp. And if you cross that threshold and make it a little sharp, you need to find a way to add mass. And so the way I reconciled it here was I super glued a little hex nut onto the end here, which added enough mass to bring it back into tune. But that's definitely something, if you're looking for just like a solid bar without any other additions, you should definitely watch out for that, and try not to have that happen. But at this point, I don't have enough material to remake this bar, so I went with that to sort of correct the tuning. So yeah, off to the next. So now we've got the full instrument. I don't have the external power supply circuitry up right now. This was just as a preliminary test. All of the bars, all the electromagnets are all hooked up to pins 11 through 22 on the Teensy. It's booted up with the updated code. So here I have basically just copy and pasted it for all the different kinds of notes. It's the same exact code as before, just now copy and pasted for 12 notes, C6 through B6. Not the most elegant solution, but it works. which is what we were aiming for. Right now, I've just loaded up this very simple melody I just came up with in a couple minutes here, just to give you an idea of what it kind of sounds like. So here we go. Get the both. So there we go. It's capable of polyphony. It's capable of different tracks as long as all the tracks are outputting to the Teensy Mini. Yeah, I mean, this is the instrument pretty much. The only thing that's missing right now is the external power supply. As you heard, it's quite quiet. And one of the issues I noticed with the board is if you have several notes, several electromagnets connected to it all at the same time, if two notes are playing at the same time, the current gets split. And so the amount of power that goes to each electromagnet gets halved or third or fourth, depending on how many notes are playing at the same time. It's something that I believe an external power supply that's powering all these magnets separately will solve, because then the Teensy output is just controlling an external power supply, and the external power supply will be able to handle several electromagnets at once. So that'll be the next step in the process. But some notes I had is it's quite difficult to actually hang this up correctly because these are free floating and quite close together. The magnets on the underside of each of the bars wants to attract each other, but if you have it set up close enough here where it's floating just above the electromagnet, then it is, each bar is more attracted to the electromagnet than it is to the bar next to it. So that solves that problem. The other thing I have here is these are just being held up by knots on each of the holes there, and so you need to be pretty good at tying knots for that to for that to hold up. So there's a lot of micro adjustments to having them hang at the correct height over and over again. I think if I were to spend more time on the mechanical design of the frame, I would add some kind of a fixture up here that I could raise and lower by very small amounts, probably with some kind of a screwing mechanism to adjust the height, so that you tie the knots and you have the string to a rough length, and then you can fine tune it with each of the notes later on. I might also look into hanging it differently. This arrangement I have because the way that the strings are holding it up gives it the most free vibration for the longest sustain, which is sort of the goal with the instrument. But something that I might consider is hanging them differently. So maybe having all the bars be strung up horizontally, and there's one string that sort of goes across all the bars to hold them all at the same height, and then you can just adjust it up and down all at once. The only thing that might come with that is I found that if the string was a little too tensioned on the bar, it would be damping the resonance a little bit. But that would be something that I would probably look into. But for now, it's just figuring out the external power supply because it's working. Everything's good. So this is the last update of the Pipe Dream project. I would say, upon reflection, the biggest draw that I had with this project was just the amount of time that I had to spend on it. I mean, I could spend several more months perfecting all the small little systems in this project, but I think that this serves as a really solid proof of concept. In terms of what I updated since last time, I added sort of a wood base to this frame to attach this onto, which gives it a lot more of a sturdy mounting system. And it allows me to attach the circuitry onto the frame itself as well. So now it's this self-contained instrument. I also replaced the solderless breadboard with a soldered breadboard, just to make sure that those connections were nice and sturdy in there. So yeah, there are plenty of recommendations that I can make for the future. And like I was saying, if I had time, I'd work on this for several more months. And all those recommendations I will include in the paper that's supplementing this project. In terms of what I could do, I wrote up this small melody. It's just going to loop, so I'll let you hear what that sounds like. So you can hear some of these bars have pretty great sustain. Um, it's very reminiscent of somebody rubbing their finger around like a wine glass. It has a very clean and bright tone. The system is contactless, so it's the electromagnet is vibrating the bars themselves. So there's no mechanical noise in the system that you would hear from something like hitting the bar or bowing the bar, for example. And so you get that just pure what the bar sounds like without any of that mechanical additions to it. So it's very sort of ethereal, dreamlike kind of a sound. In terms of its polyphonic capabilities, I just wrote this really quick. It's a C major 1 4 5 1 progression, just to give you an example of what that sounds like. So yeah, it's certainly capable of polyphony. Um, I'm gonna spend some time writing a little bit for the instrument just to get sort of the musical component of this started a little bit because as my professor reminds me, this is a music project at the end of the day, and although that I spent a lot of this time focusing on the technical aspects of realizing the instrument itself, there now it's time to do the real work, right, which is composing for the instrument. So now we have this thing that can produce this very clean glass-like sound. What kind of music can I make with this thing? What kind of music would I want to make with this thing? What kind of music can this instrument do that other instruments can't? Um, and so I'll be exploring that a little bit with the limited time that I have left, just to give sort of a hit the ground running kind of approach. So when this continues to be worked on in the future, there's a solid grounding point of what is in my head with this instrument. So yeah, it's been a good 7 weeks. Learned a hell of a lot.